Hey, Mr. Ari, and we're going to talk about exponential functions. So we've talked about linear functions. An exponential function is one that changes by a constant multiplier. The forms of an exponential function are, so here's where we see the difference. So I say constant multiplier, and you're kind of thinking linear already. Okay, but y equals a times b raised to the x. So now we see the exponential name show up, a times b to the x. Okay? Or f of x equals a times b to the x. But x there is the input. A is the starting amount now, and b is the multiplier. So we're multiplying by the same number over and over. So an example I have down here, a linear function might look like 2x plus 3. So yes, we're changing the x and multiplying the x by 2. Okay? But whatever number we're plugging in, we're just doubling it and then adding 3. And that makes it linear because it just adds 2 more each time we change the input. Whereas the exponential, a variation of that, would be 3 times 2 raised to the x. So when we plug in a number, when we plug in 5, we don't say 5 times 2 in the exponential. We say 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, or something like that. So it's doubling, okay, from one step to the next. So in the linear, the input gets doubled there, but what happens with the exponential is every time we increase x, the last value doubles, not just the doubling of the x value. So let's see this in action, or at least try to. It says a lab cultures a certain bacterium starting with 2 milligrams. So if we go back to the idea that we're saying that this could be f of x equals a times b to the x, when we say starting with 2 milligrams, why did that happen? There's something about when I get to a certain point in every file it does something weird. Okay. Let's try again. So starting with 2 milligrams. So in my a times b raised to the x, a is the starting amount, that would be the 2. And that would be the starting amount. And then it says the bacteria triples every hour. So that's what's happening. That's the constant multiplier. So from 1 hour to the next, you just look at the previous hour and you triple the value. Okay? So in that case, the b would be 3 for the triple. Tripling. And that's where we get the function that's right here. B of h, bacteria per hour, equals 2 times 3 to the h. Okay? And if we make a little table, and we'll make a very short table with this, but we're going to put in h. We're going to get back b of h. Because when you raise things to an exponent, they grow really quick. So let's see here. We're going to plug in 0, 1, 2. That should be enough. You may have to use a calculator, but 2 times 3 raised to the 0 would be 2. So look over here on my graph, and let me kind of raise it up a little bit. Here is the point 0, 2. So down here would be hours, and over here would be bacteria. And if I plug in 1, that'd be basically 2 times 3, so that'll be 6. So over here at 1, this one is to scale, how odd. 1, 6. Sometimes points disappear off my graph, I don't know why. And if I plug in 2, that would be basically 2 times 9, which would be 18. So when I come over to 2, I'm looking for 18-ish right here. So one thing you can definitely see here from the graph is it's not a straight line. Okay? And if you try to think of a straight line, and I'll put this on here and kind of erase it, but if you did the straight line between here and here, it would keep going this way, not curve up. So just kind of keep that in mind. So exponential functions has a different form. It grows a little bit differently, and it's not a straight line. So big difference between a linear function and an exponential function. So let's just kind of see if we can keep that form, a times b to the x, in mind, and write some functions from that description. Okay, here's my example. A forest fire starts out covering 15 acres. Firefighters, well, let's just go ahead and write this down. So what we know here is that the starting amount, A, will be 15 acres. A forest fire starts out covering 15 acres. Firefighters lose control and the size of the fire starts to double every hour. So doubling, that's kind of like a rate, but it's a constant multiplier. So that B will be 2 for the doubling. Write a function to determine the size of the fire and how many acres does the fire cover after 5 hours if nothing changes. So let's see here. We're going to say what we're going to have is we're going to have a function, and I'm going to call it big A for a number of acres, and the input will be H for a number of hours. Okay. So acres after so many hours. Well, then we need an A. So let's just see. The idea was f of x equals A times b to the x. So A would be little a would be the starting amount. That'd be 15. And then the change, the multiplier, is 2 because it's doubling every hour. So 15 times 2 to the h. Okay. In that case, the starting amount A, little a, is 15, and the multiplier is b is 2. So let's see. That's our exponential function. So let's see here. If we want to plug in 5, that'll be 15 times 2 to the 5th. I'm going to pick up my calculator. That's 32 times 15. I get 480 acres, which is what it will cover in 5 hours if this happens. So when we say double, that means that the 15 goes to 30, then the 30 goes to 60, the 60 goes to 120, and that's how we get here. The next example here. During a pandemic, there are 20,000 people infected with the virus when a vaccine is created. As the vaccine becomes available, the number of infected people is cut in half every month. Write a function to calculate the number of people infected at a certain month after the vaccine is available. So what do we know here? We know that the A, in this case, the starting amount is 200,000 people. And the multiplier, the rate, is it's going to be cut in half. So 1/2, or we can use 0.5 if you like. And the form that we use, f of x equals the starting amount times the multiplier raised to power. So what do we want to call this? We're going to call this I for infected people. And what's going to be going in here is going to be months. So I of m. You can call it many different things. Okay. So what do we have here? We have the starting amount, which is 200,000 times 1/2, or 0.5 for the multiplier, raised to the m in this case. So 200,000 times 1/2 to the m is how I've written my function. You can definitely use different variables if they come to your mind. Okay, so then the question is, how many people remain infected after 1 year? So 1 year, we don't want to put in 1 because this thing is measured in months. So I of 12 equals 200,000 times 1/2, or 0.5 to the 12. So one thing we should be really careful here is how we put things in our calculator. If you need help with that, get with me. But let's make sure. since we know the vaccine is supposed to help, and we're cutting this in half, that we get something hopefully dramatically smaller than 100,000. So let's see here. Excuse me, dramatically smaller than 200,000. I get, and if I round it, I'll just round it to the nearest whole number. I get 49 people still infected. Okay. Alright, looks like we got time for another one in this video. But if you need help with your calculator and figuring out how to put that in, let me know. And we'll make sure to try and point you in the right direction. Alright, example. One person on an assembly line can produce 50 items per hour. An hour. For each worker that is added to the assembly line, production triples. So if I can make 50 items in an hour by myself, if there's two of us, that's saying we can make 150 items. Okay. How many items can be produced in an hour if 8 employees work the line? So let's see if we can write this out. Once again, we're going for the f of x equals a times b to the x. The starting amount here is 50 items. And what happens was the ratio, or the multiplier, is tripling, so 3. So let's see here. We're going to produce items. So once again, I guess I'll use I of employees. Okay. I of E, that doesn't sound too good. Let's I of W for workers. So that will be the starting amount, which is the 50 items one person can do, and then that's going to be tripled for every worker we add. So 50 times 3 to the W. And then it says how many items can be produced if 8 employees work the line. Well, we might be getting out of realistic information here, but let's see. We'll just go with what the formula says. 50 times 3 to the 8th. So this is a dramatic difference. It looks like 328,050 items, which I'm going to say my function was made up in the beginning just to have something to work with. So let's don't put a whole lot of stock in how much that changed, but we did the right work. All right.